the last presentation, we looked at graphing quadratic functions in standard form. There is another form for quadratic functions. The second one is vertex form. And so let's go ahead and see what that looks like. Okay, so recall that standard form is f of x equals ax squared plus bx plus c. Vertex form, on the other hand, is going to be f of x equals a times x minus h squared plus k. For both of these, we have the direction of the parabola. If a is greater than 0, then our parabola opens up. And if a is less than 0, our parabola opens down. For the y-intercept, we have set x equal to 0 and simplify. And in standard form, remember that our x terms cancel. And we can technically take a shortcut and just write 0, c. For vertex form, this one does require a little bit of work. We do need to actually set x equal to 0 and simplify. For our x-intercepts, remember that x-intercept is where it crosses the x-axis. We want to set y equal to 0 and solve, using factoring if possible. For vertex form, we want to set y equal to 0 and solve using the square root property, if possible. For standard form, we did have some work in order to find the vertex. Remember that we wanted to use x equals negative b over 2a to find the x-coordinate, and we had to plug the result back into the function to find the y-coordinate. Vertex form, there is no work associated with finding the vertex in vertex form, hence why it's called vertex form. The vertex is h, k. Now, one thing to note is that the inside number, we want to take the opposite of whatever is inside, and the outside number, we keep it the same. We also have an axis of symmetry. In the last presentation, we saw that the axis of symmetry was x equals the x-coordinate of the vertex, or negative b over 2a. In vertex form, same thing, it's going to be x equals the x-coordinate of the vertex. In this case, it will be h. We still want to use this idea of symmetry to make sure that we have enough points in order to graph. So we're going to use the vertex and the y-intercept to find a symmetric point. Another thing that we can add in now is we can add in domain and range. We are talking about a quadratic or polynomial equation, so our domain is going to be all real numbers. And now we can go ahead and, once we have our graph, or we have an idea of what it looks like in our head, we can determine the range. The two things that are going to determine the range are going to be our k value, our y-coordinate of the vertex, and our a value. Does this open up or down? Okay, so this section is going to be divided into 3 presentations. In this first presentation, we're just going to talk about a. We're going to talk about what does the leading coefficient do. And so we're going to look at some very basic examples, and in order to graph these, I'm going to go ahead and use tables. So if we start with a, we have f of x equals x squared. Let's go ahead and look at our basic graph. So for this one, I'm going to use -2, -1, 0, 1, and 2. Okay, we're just going to square these numbers. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. Alright, so if we graph this, we have negative 2, 4. Negative 1, 1. 0, 0. 1, 1. And 2, 4. All right, if we go ahead and draw through our points, we should get something that looks like this. So what are some of the key points that we have here? We have a vertex of 0, 0. Same thing for a y-intercept and an x-intercept. So all of these are 0, 0. We do have an axis of symmetry. Our axis of symmetry is x equals the x-coordinate of the vertex, or 0. In this case, our axis of symmetry is the y-axis. Okay, so we're going to bring in those new concepts of domain and range. Our domain is all real numbers. These arrows go forever to the left and they go forever to the right. And our range is going to be 0, our y coordinate of our vertex, comma, positive infinity. The lowest y coordinate is 0, and this goes forever up. Now for the rest of these problems, not only are we going to see what happens when a is negative, but we're also going to have leading coefficients that are not 1, which we did not see in the last presentation. So let's go ahead and see what happens if we have a larger leading coefficient. If we look at b, we have g of x equals 2x squared. For this, I'm going to use my minimum number of points. I'm going to do negative 1, 0, and 1. So if we plug in negative 1, we get 2 times negative 1 squared. Negative 1 squared is 1, and 2 times 1 is 2. If we plug in 0, we get 2 times 0 squared. 0 squared is 0 times 2 is also 0. And our last one, we have 2 times 1 squared. 1 squared is 1, and 2 times 1 is 2. So here is our table of values. If we go ahead and graph this, we have negative 1, 2, 0, 0, and 1, 2. If we go ahead and graph it, we should get something like this. Okay, so again, we have our vertex, our y-intercept, and our x-intercept are 0, 0. Our axis of symmetry is x equals the x-coordinate, or x equals 0. We have our domain is, again, all real numbers. And our range is going to be the y-coordinate of the vertex, 0, comma, infinity, since this opens up. All right, last example. Let's look at h of x equals -1/2 x squared. For this one, so that I get numbers that cancel with my denominator, I'm going to go with -2, 0, and 2. So if we plug in, we get -1/2. 2 squared is 4, and -1/2 times 4 is -2. -1/2 times 0 squared. 0 squared is 0, and anything times 0 is 0. All right, -1/2 times 2 squared. We get -1/2 times 4 over 1. And again, we get -2. All right, let's go ahead and graph this. We have -2, -2 is down in quadrant 3, 0, 0, and 2, -2 is down in quadrant 4. And so now if we go ahead and graph this, remember that this does need to be a curvy V. We should get something like this. So just like in the previous problems, we have vertex, y-intercept, and x-intercept are 0, 0. We have an axis of symmetry is x equals 0. This is still a quadratic or a polynomial function. Our domain is -infinity to infinity. And our range, this is now pointing down, so it is going to be -infinity, comma 0. Remember that for range we go bottom to top. Since these arrows are going down forever, that gives me my -infinity. My top value is 0. All right, if we look at these example B and C and compare it to our basic graph, notice that not only does A determine whether it's going to be up or down, but it also determines whether it's going to be a fat or skinny parabola. If your A value is larger than 1, like a 2, you're going to have a skinny parabola. If your A value is smaller than 1, then you're going to have a fat parabola. All right, so that takes care of exploring the A value in our vertex form.